Hello everyone, welcome to this course. So my name is Zainab. I will first briefly introduce myself, then I will explain a little bit of rules and examination and content in this course, and then we will start our first lecture. So my name is Zainab. I am originally from Iran. I studied my bachelor and master there, then I decided to do my PhD studies in Sweden. So I graduated from Linköping University and my field of studies was formal verification. And now I am teaching at Uppsala University. So again, very welcome to this course. Let's see a little bit how this course is organized. So in this course, we will have 9 modules. All material will be uploaded on Studium, or the lectures will be uploaded on YouTube, and the link will be put there. So we will start by history of computers, then we will talk a little bit in the next lecture about computer architecture. So in this course, we will talk a lot about different aspects of computers. So then we will move to operating systems, computer networks, and we will have 2 lectures about programming. One is about the first one. The first programming lecture will be about high-level programming, in which we will mainly focus on Python. And in the next one, we will cover basics of assembly programming, which is a low-level language. We will talk more about what are high-level and low-level languages and why they existed, and what are their advantages, disadvantages. Then later on in the course, we will talk about cybersecurity, what attacks they are, what solutions they are, things like that. And then we will have a lecture about artificial intelligence, which is one of the common trends today, and it seems that it will be one of the main trends in the future, and it is an act to make computers more smart so that they can act or behave like human beings. And in the last lecture, we will talk about the effects of IT in our society, and we'll discuss sustainability and even ethics in IT. So for examination, I should mention that we will have 4 compulsory assignments that you need to finish, and 4 optional assignments that you decide whether or not you want to do, and the final exam, which is of course compulsory. In the compulsory assignments, we will have 2 programming assignments, one for Python and the other one for assembly. We will cover all the material and everything that you need to know to perform those programming assignments. So even if you don't have any experience at all with programming, it is not a problem. You will learn everything in this course. And for those assignments, we will have drop-in Zoom sessions so that you can join, ask your questions, and we will have lots of help for you, like tutorial videos, lectures, other material that you can self-study, and we are always happy to see if we can help you with your questions. And so 2 of the assignments are programming, and the 2 other are written assignments. And in all those assignments, you need to get at least 80% of the points so that you pass it. And you need to pass all compulsory assignments. Then we will have also 4 optional assignments, one of which is a Python programming assignment. And the points that you collect from optional assignments will be added to your score at the final exam. But doing optional assignment doesn't substitute compulsory assignments. And we have a final exam that you need to get at least 50% of the points in it so that you pass it. And in that 50%, that I mean all the bonus points that you have collected here from optional assignments will be counted. So now let's start our first lecture. In this lecture, I am excited to talk about the history of computers. It is always interesting to know what were the inventions, the discoveries, and the way that led to the powerful and digital computers that we have today. So the objectives in this lecture is to discover the age of computers and discover their implications on our history, on our societies, and see what were the important inventions and people on the way that contributed to the modern computers that we have today. So how old do you think are computers? The modern computers are not that old. They are not like centuries old, but the need for computing has always existed, and we have had computing devices, not computers, since centuries ago. So maybe the eldest computation device was abacus, which was invented in the 13th century. This is actually interesting to look at the abacus and its use because it somehow is related to the computers that we have today. So in an abacus, you can do like addition, subtraction, and you have some digits. Each of these digits can vary from 0 to 9. They are like numbers that we use these days. So it can be anywhere from 0 to 9. And it is, of course, hand operated. It needs a human being to do the calculations by hand. But what the abacus does is that it stores the state of the computation. For example, it shows you how many, what is the value in the first digit and the next one and the next one. The fact that it stores the current state of the computation is somewhat like what your hard drive does. In your hard drive, you store what is the current data that you have. So it's a much simpler version of that. And these were invented, the abacus, because the societies were getting bigger at the time, and the computations would not be simply done by just the human brain. So they needed to store the computation state somewhere and then work on it, for example, to know how many cows there are and how many, people there are in the town and so on. And then they could simply do mathematical operations on them. Each row in an abacus is a different power of 10. It's like the numbers that we work in real life. So the first place counts the number of ones, here I mean, and then the next one we count the number of tens, and the next one we count the number of hundreds, and so on and so forth. So abacus was not the only computation device in the history. There are many other computation devices. One of the very old ones is called astrolabe, which enabled the ships to calculate their latitude at sea. Another one was called slide rule, which was capable of doing multiplication and division. And there were hundreds of thousands of clocks that were used for different purposes. For example, for calculating sunrise, sunset times, for calculating tides, or simply for showing the time, or calculating positions of celestial bodies. But the first real calculator was invented by Pascaline, which was the first accurate mechanical calculator, and it was invented in the 17th century. It used gears to count by tens. So instead of the rows and that we had in abacus, we have here gears. So the first gear shows the number of ones, the next one shows the number of tens, the next one the number of hundreds, and so on. And the value of the gear goes from 0, 1, 2, 3 to 9. And each time a gear reaches 9 and want to increment by 1, then it makes the next gear to advance by 1, and the gear itself resets to 0. It's like what we do in our additions. So it could do addition, subtraction, multiplication, and division. It had a basic design that was used in mechanical calculators for 300 years. This is amazing. Imagine something is invented today and is used for 300 years. This is almost impossible in today's world with the fast rate of different inventions. It is not imaginable for us. But in those times, the speed of different inventions was much less than today. So an invention like this calculator could be used for over 300 years. So in those times, there was no electricity, so all these computations was mechanical. The term computer was not used for these devices. It was actually used first in 1600s for a job title, and it meant people who worked with some calculation that worked with some computation device, like, for example, a calculator or something like that. And then they would do some computation, and other people in the society or different organizations would use their results. And this title persisted to be set to human beings until 1800s. So these devices that were used for computations were handcrafted, so they were expensive. This was not very common that people would have them in their homes. And doing real world problem computations would require many computational steps that could take like days or weeks. Imagine you would need to calculate in military, for example, how you should use your military devices, in which you need to take into account many variables. For example, the speed of the wind, your geographical place, your distance to the target object, and so on and so forth. All these are variables that you need to take into account in your computation. And just using a simple calculator to lead you step by step through your calculation would be very time consuming. So for this reason, the human computers that we just saw in the previous slides were working to create pre-computed tables. So for example, you would have a book that had the results of multiplications in it. Then if you needed to multiply several large numbers by each other, instead of using a calculator, you could go to this book and in a few minutes or seconds, find your results. So there are various pre-computed tables for different computations, for different devices. For example, in the military, there were different tables that were called range tables that used to, for example, tell the soldiers the angle to set the cannon in order to hit their target. But the problem with these range tables was that they very much dependent on the design of the device that was used. So if a new device was invented, or if the device would change a little bit in its design, then they needed new tables. But then this would require a lot of work by human computers, and this would be very time consuming and very expensive. So some solution was very much appreciated. So before we see what steps were taken to solve this problem, I want to introduce here polynomials. Many of the problems that we have in our real life can be modeled as polynomials. Polynomials describe the relationship between several variables, for example, range and air pressure, etc. And they can be used to approximate logarithmic and trigonometric functions. Here you can see some samples of polynomials. So these polynomials would be used a lot to approximate real life problems. And if you had a simple calculator, it would be very difficult to use your polynomial step by step to do all the multiplication and division, subtraction, addition, etc. So a device would be needed to calculate the polynomial as it was. So for this reason, one of the very intelligent people that was called Charles Babbage actually designed a machine called the difference engine. Difference engine was a complex machine to approximate polynomials. Here in this figure, you see his design of the difference engine on a piece of paper. So first he designed his device on paper, and then he started to construct it at 1823. And this his design consisted of over 2,500 components. So he tried over 2 decades to put all these components together, but unfortunately he wasn't successful and could never finish designing this device. But later on, from his drawings, historians could actually finish production of the device, and it actually worked correctly for approximating polynomials. But his work wasn't wasted, so his designs and ideas were later on used in modern computers. So even at the time he was working on difference engine, he was thinking about another machine, which was called analytical engine. Analytical engine was not just for approximating polynomials, it was actually a general purpose computer, meaning that it would do different sorts of computations, not just polynomials, and not just for a particular computation. And it would be given data, and it would run operations on them in sequence, and it had even memory and a primitive printer. It is actually most of the things that our computers have. So it was much ahead of its time, and it was never fully constructed, but it inspired the first generation of computer scientists. For this reason, Charles Babbage was called the father of computing. And Charles Babbage had a colleague who was called Ada Lovelace, and she actually wrote hypothetical programs for the analytical engine. Although analytical engine was not built, but Ada Lovelace and Charles Babbage knew how it would work and what would be the inputs to it, and how it would get instructions and so on. So Ada Lovelace started to do programming on it. So she did programming long before the advent of the first computer. This is very remarkable. So she did programming already in 1852. We will talk a lot about programming in this lecture, but it is very interesting to see that she did programming and used variables, instructions, etc. in her programs, although there was no computer at the time. So as we were going forward in history, at the end of the 19th century, computing devices were used for special purpose tasks, for example, for science, engineering, military purposes, etc. But they were rarely seen in businesses or domestic life. Maybe just in government they were used. But the need for computing would get more and more every day. So one of the very interesting examples that needed really the need of computers or computation devices for doing computation was this event? So the story is that U.S. government faced a serious problem for its census at 1890s. So U.S. government would run census every 10 years. So the last time they had done census was 1880, but since then, their population had grown so much due to immigration. And they had seen that already at 1880, their census took 7 years to manually compile, meaning that after they had collected all the information from the people, etc., in their country, just to summarize all that information and extract data from that took 7 years because it was done manually. So then for the year 1890, they had a real problem. They realized that because the population had grown so much, just compiling the census data would take 13 years. And it was it would already be outdated because in every 10 years, they would need to do a census. So having 13 years to just compute the result of a census would be just too much. So for these reasons, the Census Bureau turned to Herman Holleris because Herman Holleris had designed a machine that seemed to be useful for census. Let's see what this machine was. Herman Holleris has designed the tabulating machine at 1890s, which was electromechanical. This is interesting, so that this invention was done like 10, 11 years after the invention of electricity. So this is the first occurrence maybe that electricity was used for computation. So his machine was both electrical and mechanical. The technology had not evolved at that time enough so that a machine would be just purely electrical. So that machine used traditional mechanical systems for keeping counts. It had like gears and so on, like Pascaline calculator, but it coupled them with electrically powered components that helped it to read data automatically. And the data was collected in something called punch cards. Let's see what punch cards mean. But before that, so please pay attention that those times, I mean, if they just collected the information on a piece of paper, they could not use it by a computation device. They used punch cards in order to find a way to feed the information to the computation device so that it would understand somehow. So what are the punch cards that makes them special? Punch cards were some cards that first used in fabric industry to automatize weaving complex patterns. They are simply paper cards with a grid of locations that can be punched out to represent data. So here you see what a punch card for the tabulating machine looks like. For example, it has some dots for the marital status, some dots for age, etc., etc. And then, for example, imagine the marital status. If someone is married, then the corresponding place for the married status would be punched out. Then these cards were fed into the tabulating machine, and then when the machine was reading these cards automatically, it would find the holes in them in different places. And then it would put a wire into those holes. Then some specific circuits would be completed. For example, the circuit for married people would be completed. So a machine would know that we have a person here that is married. So then this would make the device to increment the number of married people by 1. Later, so the first use of these punch cards was to give input data to the computers, but they were actually used for decades for computers to, for example, give data or to even do programming. So the programming, we will discuss a little bit more in the coming slides, but they would use punch cards in this way. So they would first maybe write their programs on a piece of paper, and then they would punch their programs into punch cards, and then these punch cards would be fed by a human operator to the computer. So the programming was even done first using the punch cards. So let's see what the results was. Here you see some people that were working with the tabulating machine and with the punch cards, and punch cards are fed to the machine and so on. So using the tabulating machine was 10 times faster than manual tabulation. This is amazing. So the census, instead of taking 13 years that it was approximated to take, it took only 2.5 years. So it saved the census office $1 million. After this case, which was very amazing, it inspired many people. So businesses, organizations began recognizing the value of using computation devices and saw that they can improve their labor and data-intensive tasks by using them. So there was a huge demand on, for example, buying tabulating machines or other machines that were used for computation and were invented at that time. So Herman Hollerith started the tabulating machine company 6 years later, and then later it was even changed to the name International Business Machines Corporation, which is the IBM company that I'm sure all of you have heard of. So after Herman Hollerith, we have Alan Turing, which influenced the world of computing a lot. At 1936, Alan Turing presented the notion of a Turing machine. It was a machine that was capable of computing anything that is computable. This is amazing. So the central concept of modern computers was even based on the idea of Turing machine. So his idea was abstract, but it was built later on. And so a Turing machine could perform logical operations, and it could read data, write them. So this machine has a tape, an infinite tape. It can read data from the tape. Here, there is a big 0 on it. Let me run this video. I don't know why it doesn't run. Okay, never mind. So on this infinite tape, the data can be written on by this head here, and then they can be read from, or they can be erased by this eraser here. So actually, it is interesting that this idea is also used in modern computers, and the RAMs of our computers works very much like the tape here in a Turing machine. So for this reason, Turing was called the father of modern computer science. He actually had created a machine that was designed and manufactured and was used to encrypt the communications during the war. And it was shown in a movie that was called The Imitation Game. So he was one of the big contributors to the computers. So we are not still in the era of modern computers. We are just before that. But there are, these inventions are very important to talk about because they influenced a lot the modern computers that we have today. So one of the very important inventions was the machine that was called Harvard Mark I, which was created at 1944 by Grace Hopper and Howard Aiken. It was one of the largest electromechanical computers. So at this point, we have computers, but they are not yet totally electrical. This machine was electrical and mechanical. So it was too big, as you see here, it fits in a very big room. It had over 700,000 components and 3 million connections to connect those components together and 500 miles of wire. This is unbelievable. So this computer was used by US Navy for ballistic and gunnery calculations during the Second World War. And in this computer, the main electrical component was called relays. Actually, what is the main electrical component in the computer is very important in the design of computers, and actually improving the electrical components in the computers is the main reason that the computers have become better and better during time. So we will talk a lot about the electrical components in this lecture and how they changed. So let's see what relays. Before that, let's see what is the architecture of this computer. So now that we have real computers, we will talk about architecture of computers. Architecture of a computer is like architecture in other engineering fields. It talks about what elements are in a computer and how they are interconnected. So in the architecture of the Harvard Mark I computer, we had these elements as you see here, and it is interesting to know that all of them exist in nowadays computers. So here in the middle, we have this part which is called Central Processing Unit. It is the CPU that we have in our computers as well. So in the CPU, there is arithmetic and logic unit that does all the arithmetical and logical operations. And we have a control unit, and we have some special memories that are faster than other memory in the computer, and these are used inside the CPU. Modern CPUs also have these. These are called registers and program counter. So all this is the CPU, which is like the brain of the computer. It does all the processing needed. So for example, in modern computers, showing a picture or rendering a video or playing some game, all needs a lot of processing. That is, for example, done by Central Processing Unit or CPU. And then besides CPU, we have the memory of the computer. What is important about the Harvard architecture is that it has two separate memories for the program, meaning for the instructions that need to be executed, and for data. So there are two memories, and for reading from these memories, in our computers, we have wires that are called buses. So these are buses so for example, this one is called the data bus, which means that when you want to read a piece of data, it carries the data in a wire and then passes it to the CPU. And for the instructions of the programs, we have instruction bus that carry the next instruction that has to be executed, for example, to the CPU. So then CPU takes the instruction and takes the data, and on them it does its operation. And we have two other buses that give the address of the thing that needs to be read from the memory, because the memory in a computer has many small places and all of them have a unique address. So first there is a bus that says, okay, what is the address of the instruction that you want to read, for example? And then there is another bus that carries the instruction and delivers it to CPU. And for the data, it is the same concept. So there is an address bus that says, where is the data that you want to read? And then when it is read, another bus carries the data and delivers it to the CPU. And besides this, we have the input-output system. For example, a system that gets the punch cards and read them, or in our modern computers, the monitor, keyboard, printer, all will come here. They are input and output devices. So in Harvard architecture, we have separate storage and separate buses for instruction and data. And CPU can access instruction and read-write data at the same time because it has different buses for them. This is very important to know about the Harvard architecture. So at the same time, a CPU can fetch instruction and fetch data. But there is another architecture I will show you in the coming slides that doesn't have this property. So the components we have already discussed about, we have data and instruction buses that deliver data and instruction to CPU. We have registers, which are these fast memories, fast and small memories inside the CPU that help with the arithmetical operations. And we have program counter, which says what is the next operation or the next instruction that should be executed. And we have the control unit here and the input-output system. So Harvard architecture was later on modified a little bit, and it was called the modified Harvard architecture, in which it uses the same memory to put data and program. So data and program would be in the same memory. For example, we have a little bit of data and then a little bit of instructions, and again, a little bit of data and so on. So it gives a little bit of more freedom, but it is still in this modified architecture, still the buses are separate. This is actually used in modern general purpose computers nowadays. In our computers, we are using modified Harvard architecture. So let's see now about the electromechanical relays that were used in Harvard machine. So we said that this machine was based on relays. So you can see how a relay looks like in this picture. And here is a graphical diagram of it. So relays are simply switches. They are mechanical because they have parts that move, but they are electrically controlled. So let's see a little bit how they work. So here you see they have a wire that is called the control wire. Whether or not there is electricity flow in the control wire determines whether or not the circuit is open or closed. So this relay will be used in the computer and will be connected to the other elements in the circuit. In electrical circuits, we have wires, we have resistors, capacitors, diodes, and relays in this case. So all these are connected. So relay is part of a large circuit. And from this ends, this and this, and this end, it is connected to other elements in the circuit. So when electricity current flows through the coil, an electromagnetic field is created, which in turn attracts this metal arm here. Let me show it, this metal arm inside the relay to shut and complete the circuit. So then this will be something like this. So this mechanical arm will shut down. So then this becomes like a complete wire. So the electricity can flow through it and the circuit would be complete. So you see a relay has two different states. In the state in which it is open, so the circuit is open, meaning that the electricity cannot flow from one side to the other side. There is no flow here, for example, but it has another state in which it is closed, so the circuit is complete. These two states were actually used in computers to count. So you know that in computers, we have always zeros and nines. The reason for that is that the devices, the underlying devices that are used for construction of computers have always had two states, 0 or 1. So relays were used for a short time, but later on we will see that some devices were created which still had only two states, 0 or 1. And we will actually see in the next lecture how these zeros and ones will be used to count the numbers, the natural numbers that we use every day, because we are not used to counting with zeros and ones. We use 0 up to 9 in the different digits of the numbers that we work on a daily basis. Working with only 0 and 1 seems a little bit too much limited, but we will see in the next lecture how it works. In this lecture, what we're concerned about is that what is the device that captures these zeros and ones. The first devices for those purposes were relays. So from this point on, we don't have the gears, the mechanical gears anymore in the computers. Instead, we have these electric controlled elements. So we don't need human beings to, for example, turn on a relay. We have electricity that can turn on or off the relay. This was a huge invention that actually made electrical computers possible, and it was improved a lot over time. So a relay simply is like a water faucet. The control wire is like the faucet handle. When you put electricity in it, it will close the circuit. When you don't let electricity go through it, it will be open. So a good relay in 1940s could flick between the open and shut state 50 times per second. This might seem a lot, but because these relays were used in computations and computations needed to be fast, this speed was actually not good at all. 50 times per second is very low. So the Harvard Mark I computer was very low. It would take for it 15 seconds to do a division. In terms of the computers that we use today, it is just too slow. It was even too slow at that time because the division was not the only task that the computer would do. It was used in military and they had many sophisticated operations. And too many of the operations were needed for a complete program to compute. So if a division would take 15 seconds, it would be just too slow. And another drawback of it was that it was mechanical, so it would wear and tear, and it had many relays. And when you have many relays, it is possible that some of them fail. And it had actually over 3,500 relays. So it was too many, and it was very probable that one of them could fail. So then the whole computation would fail. And these electrical machines would consume a lot of electricity. So then they would get very warm, and the heat was itself a problem, how to cool down these machines. Actually, there was another problem that was not expected, and it was that these warm and dark machines were interesting for insects. So there was a time when Hopper noticed that their computation is not done correctly, and they checked many sort of things inside the computer. They didn't find the problem until at the end they found an insect which was on one of the relays and was dead, and it had resulted on the problem. And they, in the report, actually they taped the insect. So later on, Grace Hopper said that each time we had a problem with the computer, we would first say that there is a bug in the computer. And interestingly, this term is still used commonly in the computer context. For example, whenever you write a program and you see there is a problem and you don't know where it is and you're looking for it, you say, oh, there is a bug in my program, or my program is buggy. Or if you have a piece of software that doesn't perform as expected, you would say, okay, this software seems buggy. Yeah, so this is how this term was used in IT. So we saw what was the problem with relays. They would wear over time. They were not much reliable. They were slow. So after the invention of relays, we have the invention of vacuum tubes. What is very interesting about vacuum tubes is that they are totally electronic. They are switches like relays, but they are not mechanical anymore, meaning that they don't have moving parts anymore. So they also control the electric current flow, but without needing to move any parts. So for this reason, they have less wear, and they could switch between on and off state or open and shut state thousands of times per second. Compare it with relays that could just switch like 50 times per second. This is amazing. So they got much faster. So these are the reasons why computers, for example, got faster over time. It all goes to the basic building elements of the computers, which were, for example, vacuum tubes at the time, and then later on they became transistors and so on. But vacuum tubes had still drawbacks. They were fragile because they had this glass bulb. They could burn out like light bulbs that we have, and they're very expensive. So a radio would need just one vacuum tube, which was fine, but a computer would need hundreds of thousands of them. So the computers at the time were not affordable for human beings. Just maybe organizations had them. But invention of vacuum tubes started the era of modern computers, because now everything is electronic for the computations of the computers, and we don't have mechanical parts. So after invention of vacuum tubes, we have switches that are electronic. They are not anymore mechanical and electronic like relays. They are purely electronic. So it means that in the circuits inside a computer, we don't have any mechanical parts that have to move. This is a huge breakthrough. So this set the stage for the first generation of computers. So far there have been 5 generations of computers, and in the rest of this lecture, we will talk about these different generations. So in the first generation, the biggest event was the shift from electromechanical computing to electronic computing. So of course, the main electronic component in this generation inside the circuits of the computer was vacuum tubes, and the memory and all other aspects of computers have evolved during between these generations. So we will take a quick look at all these different aspects. So the main memory in the first generation computers were magnetic tapes and magnetic drums. And the programming language, meaning that the language that with which one would specify the instructions that a computer would execute, was machine language. We will see more in this lecture and in our programming lectures that programming languages have different levels. The lowest level is machine language, which is in terms of zeros and ones. It is not like a real language that one could read and understand. Only people that are specialists inside a specific model of computer could understand the machine language. And it was actually quite time consuming even for them to write such programs and understand them. So the language at this first generation was machine language. And these computers would consume a lot of power and generate a lot of heat. So they were maybe as big as a room, and they were slow, and they needed air conditioning because there was too much heat produced. And for input-output devices, they had punch cards and paper tape. So there wasn't any monitors and keyboards back then. There is a huge, there is a journey to go from punch cards to monitors and keyboards that we have today. And in the first generation, there were only about 100 different computers produced, different computers. So one of these machines was Colossus Mark I, which was invented in 1943. It used 1,600 vacuum tubes. You can imagine putting all those together can be so big. And this machine helped to decrypt Nazi communication during the war. And it was the first programmable and electronic computer. So before this computer, we had the Harvard Mark I computer, but it wasn't purely electronic. It was mechanical and electronic. And programming this machine was done with logging hundreds of wires into plug boards in order to set up the computer to perform the right operation. So these people that you see here are those that work with the computer, and they had to plug and unplug wires to give instructions to the program. So while this computer was programmable, it still had to be configured manually to perform a specific computation. They couldn't give a program and expect it to automatically execute it. It was far away from that. The next very famous computer was called ENIAC, which stands for Electronic Numerical Integrator and Calculator, which was invented 3 years later on. And it used even more vacuum tubes. It had 18,000 vacuum tubes, and it was the first truly general purpose programmable electronic computer. So the previous computer was used for decrypting messages and so on, but this one was general purpose. The computers that we use today are general purpose, meaning that they can do many different sort of things. The computers that were called the general purpose at the old times, of course, were not as capable of the ones that we have today, but meaning general purpose is that they weren't built for just a very specific task. They could be given different tasks. And this computer was high speed, had high speed. It could do 5,000 10-digit additions or subtractions per second. Compare it with Harvard Mark I, which required 15 seconds to just do a single division. But the ENIAC had its own drawbacks. Of course, you can see that it was too big, it was clumsy, and it filled a large space of 1,800 square feet. And something that was very bad about it was that the vacuum tubes could fail. And since it had over 18,000 vacuum tubes, even if a vacuum tube would not so often fail, but since it had too many of them, the failures could happen very often. So imagine a computation would take several days, and then in the middle of it, some vacuum tubes would fail, and then the whole computation had to be restarted. So around this time, John von Neumann outlined the architecture of a stored program computer. He was one of the leading figures when it comes to designing computers and processors, and his ideas have been used even today. So he talked about the architecture of a computer in which, as opposed to the Harvard computer architecture, data and program would be in the same memory. And his design also eliminated the need for clumsy methods of programming, such as punch cards and paper. And his design led to the invention of EDVAC, which was the first stored program computer. So before this design, the programs were fed into the computers, either using punch cards or with plugging and unplugging wires and so on. But he had some ideas that a program would be stored inside the computer, and then the computer would execute it automatically by fetching the instructions from the memory and executing them. So von Neumann came up with his own architecture, which has the same physical memory address for both instructions and data. And in his architecture, there is the same bus for fetching data and instruction and for carrying their address. This architecture was cheaper than the Harvard architecture, but its drawback is that CPU cannot at the same time access both instructions and data, because a bus can be used to fetch one thing at a time. So once it fetches the data, the other time it fetches instruction and so on. So they could not be done at the same time, but it was cheaper. And the components that there are here are the same as the Harvard architecture. Like you see, there is a CPU, there is a architecture and logic unit, there are the registers, program counter that says which one is the next instruction to use, and we have memory, buses, and input-output system. One of the famous computers in the first generation was called UNIVAC, which was invented in 1951. UNIVAC stands for Universal Automatic Computer. It was one of the first commercially successful digital computers. So the computers before that were mainly used by military and so on. They were not commercialized, but UNIVAC was commercially successful as well, meaning that organizations realized the fact that computers would be much useful in their time. They were interested in buying them. So they bought UNIVAC maybe at that time. UNIVAC operated on magnetic tapes, no punch cards anymore. And it was the last computer actually to use vacuum tubes, because there was another invention that changed the world. Let's see what it was. It was the invention of transistors. So transistors are yet another electronic switch, like vacuum tubes. They are electronic switch, but what is remarkable about them is that they use semiconductor material. So semiconductor was discovered and then which led to the invention of transistors. So semiconductor material is a material that sometimes can conduct electricity and other times it can resist it. So it can have two different functions. For example, metals are conducts, but glass is resistor. So semiconductor can be sometimes like conducts and some other times like resistors. For example, if you apply high voltage to them, you can be like a conduct, like a copper wire, for example. But if you apply low voltage to them, close to zero, they can be like glass, so they resist electricity. This actually is very interesting. So in this way, they can be like switches to be on and off. So this semiconductor material was used to separate two electrodes. So here we see inside the transistor. So these two are its electrodes and they are connected to the semiconductor material. So as I said, if you apply high voltage to the semiconductor material, it acts like a conduct. So then electricity can flow from one side to the other side. But if you apply low voltage to it, then it will be like a resistor. So it doesn't allow electricity to flow through. So it becomes like a switch that goes on and off. Transistors replaced vacuum tubes because of their size. You see, they are much smaller. They were much cheaper and even much reliable. They didn't have anymore these fragile glass bulbs. And so in their construction, they have 3 terminals, as you see here, these 2 electrodes and this semiconductor part that are connected to wires, and they will be connected by these 3 terminals to other parts of the circuit inside the computer. And they could actually switch between on and off states, something like 10,000 times per second. Vacuum tubes could do it like 1,000 times or so. So transistors were way better than vacuum tubes. So this is how transistors are graphically represented. The base is the part, the terminal, which is conductor to the semiconductor material. And these 2 terminals are for these 2 electrodes here and there. So if you apply high voltage to base, then the semiconductor material would act as conduct. So it lets electricity to flow from the input to output. Otherwise, it doesn't. So it will be like a switch. So transistors led to the invention of the 2nd generation of computers, which last about a decade from 1950s to 60s. So at that time, computers had circuit boards inside them that were filled with individual transistors. This is important to emphasize. So the transistors at that time were individuals. And the memory that the computers used was magnetic core. The programming languages had evolved, so machine language was not often used. Instead, assembly language was used. We have a whole lecture about assembly programming. So it is a bit more human readable as opposed to machine language, which is only ones and zeros. The machines in this generation had lower power consumption compared to the previous generation, the 1st generation. And they generated less heat, and they were smaller in size, and they were much faster and much more reliable. So they were best in any aspect you could imagine. And for input-output devices, some of them still used punch cards and some other used magnetic tapes. Let's see some of the computers in this generation. So IBM soon transitions after invention of transistors. It transitioned all of its computing products to transistors. And it actually brought transistor-based computers into offices and eventually homes. But in this generation, we don't still have PCs at homes, but the trend started at this generation. So one of the very famous machines of IBM was IBM 608 calculator, which was the world's first all-transistor calculator. You see, it was still too big, but not big, as big as a room. And for memory, it used magnetic core memory. Here you see a sample of a magnetic core memory, which has, in this picture, it is 32 by 32 cores, meaning that at each row there are 32 cores. Each core is like 1 bit, so it can be either 0 or 1. So this was used for the memory of these machines, and they were programmed using a control panel. Another famous machine in this era was Tradic, which was invented in 1954 at laboratories. It was the first transistorized computer in the USA. There were other machines in UK and Australia, I think, that were transistorized, but it was the first one in USA. And it was built for the United States Air Force, and it was programmed by plug board or punch card. So you see this computer, I think he is programming this computer by plugging and unplugging stuff on the plug board. And the other way was to pass the programming to it using punch cards. Tradic was not as fast as vacuum tube computers of the day.
So we had yet another invention after invention of transistors, which was also very, very important. So at the time that we had transistors, the circuits were used by having wires and connecting transistors, resistors, capacitors, diodes, etc., all by wires at the circuit boards. But then integrated circuits were generated that actually were complete circuits, but at very much smaller size. And they were invented because before their invention, something was discovered or invented that some scientists realized that instead of using wires, they can use very thin metal passes. So then using them inside an integrated circuit means that these are the metal passes. So they had several transistors and resistors and capacitors, everything in a miniature size. And instead of wires, they had these thin metal passes. So everything was miniaturized. So you could have a miniature circuit, which was pre-built, and it was called IC. For example, you can even today buy an IC that sums up two numbers. So it's a whole circuit, but it is very small in size. These were a huge breakthrough, actually. So ICs had many transistors inside them, starting from 10 or so, and nowadays there are millions of transistors inside an IC. So they made, they resulted in circuits that were orders of magnitude smaller, faster, and less expensive. Compared to those ones that had discrete elements. They are smaller, this is trivial, but why are they faster? Because for circuits, the path that electricity has to go through affects how fast the circuit will be. So if the electricity has to go through a very long wire, it will be slower. But in this IC, the passes were much shorter than the previous circuits, so they got even faster. It's like traveling. If you would travel a shorter path, you would get to destination faster. So here, because the passes are much shorter, the computations are much faster. So they were even less expensive because maybe they required less material and metal and etc. So they were cheaper. So this resulted in generating computers that were smaller and lighter and cheaper, which was great. So then this brings us to the third generation of computers, which lasted about a decade, starting in 1960s. And the main electronic component at that time was, of course, integrated circuits. So ICs at that time were used for processing, were used even for memory. But some of the computers in this generation had still large magnetic cores or magnetic tapes. And for programming languages, we have higher level languages. So in the previous generation, if you remember, assembly language was used, but at this generation, we had languages like BASIC or Pascal, which some of you might have heard of. So the computers became, again, smaller and cheaper and more efficient compared to the second generation computers, but the computers were still costly to have, like personal computers. They were very expensive and they still needed air conditioning. But they were faster and more reliable than the second generation computers. And for input and output devices, we have some advancements here. So Here we had the first keyboards and monitors and printers. Let's see some of these machines. So IBM S or IBM System 360 series were very famous in the third generation. They were a family of mainframe computers. Mainframe computers are computers that are used in, for example, organizations and so on. They are very powerful and they have to process a lot of data that belongs to the organization. They are not like personal computers. They are much bigger and much more powerful. These series of computers were the first to cover both commercial and scientific application, and there were different models of computers in this series of computers, and the best of them had up to 8 megabytes of main memory. We will talk about in the next lecture what is bit and byte and so on. But nowadays, the main memory is in terms of terabytes, usually megabytes is very small. This series of computers were commercially very successful. Here in this picture, you see one of these computers. So this huge red box here is its CPU. It has many keys and plugs here for controlling it. And then, so this board here is called the operator's console. And on the left-hand side, we have tape drives, which are magnetic, and we have also disk drives here. So this is the computer, and these are called its peripherals. So we have seen so far how we moved from relays to vacuum tubes to transitions to ICs. So as I said before, ICs have a circuit inside them which has several transistors which are essential for electrical circuits. Moore was one of the scientists in this era, in the somewhere in the third generation of computers. He came up with his law, which was called the Moore's law. So he took a careful look at the inventions at the technological inventions during history and how computers had evolved during time and so on. And he guessed that the number of transistors inside an IC would double every 2 years. This was his guess. This law wasn't made based on any experiments and so on. This was his guess. And interestingly, it actually has been true for a long time. So here you see the transistors that were created by different corporations, for example, Intel, Motorola, etc., etc. So in the beginning, they had like a few thousands of transistors inside them, but as we went 2 years forward, they doubled in the number of their transistors. Almost they doubled. Sometimes they were even more. So when the number of transistors in an IC gets more, so the computer becomes faster because the transistors get closer to each other. So the data has to go through a shorter path, so it would go faster. So, and also the computers would get much cheaper and what else? Faster and cheaper. Yeah, this was the main implications. So after the generation of ICs, we have the invention of microprocessors, which were introduced by Intel Corporation. Microprocessor chips are the most sophisticated type of ICs. So ICs have inside them a circuit. Microprocessors are like them. They have a circuit, but this circuit is so powerful that it acts like a CPU. and it has like millions of transistors in it. Intel and Motorola became leading manufacturers of microprocessor chips. So we are here in this generation. So the whole processor now fits inside the chip. This is remarkable. Imagine in the first generation, you had to put like thousands of vacuum tubes with a lot of wires and other electrical elements to build up a very simple CPU. But at the fourth generation, you could have a sophisticated CPU that fits inside the chip. So fourth generation of computers starts from 70s and lasts until today. The main electronic computer is called VLSIs, which stand for Very Large Scale Integration. And we have also microprocessors. So in VLSIs, we have like thousands of transistors. And in this era, the memory started to use semiconductor memory as well. So before that, the memory was mostly magnetic cores, magnetic tapes, magnetic drives, and so on. But from the first generation, we have semiconductor memory. Basically, the RAMs in our computer and ROM are semiconductor memory. RAM stands for random access memory, is a memory of your computer that temporarily stores programs and data. And it is volatile, meaning that each time you turn off your computer, the data on it will be lost. We have also RAM, which is called read-only memory and permanently stores data and programs. This kind of memory is called non-volatile, meaning that its contents are not lost when you turn off your computer. So RAM usually stores some some information that the manufacturing factories store on it, and they will never be changed. So it is called the read-only memory. It's a small memory that will never be changed and is unique to each model of a computer. So in the first generation, we have many advancements. The speed of inventions at this point are very much, it is not like previous generations that were just one or two big inventions. Here we have many things. So for example, programming languages evolved a lot. We have much high level languages like Python, C#, Java. So take a look at this diagram. So at the lowest level of programming languages, we had machine language introduced in the first generation. Then we had assembly language, which were more human readable. So we call them high level language, more high level, which were introduced at the second generation. Then we have less high level languages like C and Pascal introduced at the third generation. And now we have like Python, C#, etc. at this generation. So the programming with high-level languages is easier and they are more human readable, but they were more, they require more intelligent computers. This is why we didn't have them from the beginning. So the size of these computers in this generation, of course, was smaller compared to the previous ones, and they were cheaper and more efficient, and they were faster. And for input-output devices, we had still keyboards, and but like we had the new pointing devices, optical scanning devices, and monitors and printers. The networks of computers were introduced in the first generation. A network simply means that a group of two or more computer systems get linked together and can exchange information. Before appearance of networks, computers would be totally standalone. If you needed two computers to communicate with each other, you had to store the data from one computer on, for example, a magnetic tape or something, and then transfer it to another computer. So it was impossible at that time to have computers that directly connect to each other with some sort of wire and so on. So the networks were invented at this generation because the computers became smaller. There were many computers, and in terms of technology, there were many advancements. And in the telecommunication industry, we had many advancements. So it made it possible to have networks of computers. There are other advancements. So the computer hardware was developing and MIPS processors came to market. In our assembly programming lecture, we will actually program one of the MIPS processors. And in terms of programming languages, we saw that from machine language on punch cards, we came to coding high-level languages. And more interestingly, at this generation, we have the advent of operating systems. So before this stage, we didn't have any operating systems. The computers were operated by human beings. They would feed all the instructions inside the computer, and when a program was done executing, they would feed to it the next program and so on. But at this point, operating systems were designed and were born somehow. We have a whole lecture about operating systems, and we will see what are the different functionalities and why they were added to them. It is very interesting. So the early programs and data were saved on audio cassettes, interestingly, you see here. And then floppy disks were introduced. And so because of these advancements, programs could be saved on floppy disks or audio cassettes. So operating systems were developed, because when you write the program for an operating system, you want to always have it. You need to store it somewhere. Before this, the programs were not stored on the computer. You had to each time feed them to the computer. If, for example, you turned off your computer and you turned it on again, you had to feed your program again to the computer. But at this point, because program could be stored, we could have operating systems. Operating systems are specific to the chip that makes the computer. For example, Apple computers have their own operating system. At that time they had Motorola chips, and they had an operating system which was called DOS, which stands for Disk Operating System. Then the PCs were introduced by Intel that had Intel chips, and they had their own operating system. And Microsoft developed its own operating system, which was called MS-DOS for IBM PCs. We had more advancements in this generation. We had software application explosion, because now at this point, programs could be saved on the computer. So software applications could be born. So you could have a piece of software that you develop and sell it to others or share it with other people. And we had the first graphical user interface devices, or GUI for short. Before that, if there were displays, they were not graphical. The Apple computers were the first ones to have GUIs. At this generation, the fourth generation, we have the first personal computer that was called the Altair. The fact that it could be personal was that it was small, and it was cheap enough so that individuals could afford to buy it. This computer was sold as a kit, and it didn't have any keyboard or monitor. Maybe adding them would make it more expensive, I don't know. But it didn't have them. It had only keys and lights. Bill Gates and Paul Allen were among the first owners. And Bill Gates and they together wrote a compiling program for it. Compiling program is a program that takes a program language, that takes a program and translates it to the machine code that the computer understands. We will talk about it in our programming lecture. So you see here, this is Altair 18800. It had only some keys that you could use to give it the inputs, and it had some lights that could show you the output. And actually, the first computer game was introduced with this personal computer, which wasn't very easy. You had to press a series of keys, and you could see the output of your game as a series of lights turning on and off. Then in this generation, we have the first Apple computers, Apple 1 and 2, which were developed in late 70s, and they were built by Steve Jobs and Steve Wozniak. And their operating system was stored in their ROM. ROM stands for read-only memory. We had other personal computers as well. IBM created the first computers that were called personal computer, PC for short. They were small computers, and they started at over $1,500, and they were called the machine of the year. And interestingly, we have the first portable computer here, which is called the Osborne. It cost over $1,700 at the time, but it weighed 12 kilogram. It wasn't that portable, but still. And its screen was only 5 inches. It didn't have any battery. It didn't have any installed software. So you could feed the software to it using floppy disks, I guess. Then we had the internet boom. So the first browsers were developed. The very first browser was called the Mosaic browser. Then there was Netscape, and then in 1995 we had the first Microsoft Internet Explorer. So the first browsers were very clumsy. They didn't have like pictures. They didn't have links to other pages. They were very limited, but then of course they evolved a lot during time. So now let's talk about the last generation, which is the 5th generation. It is the generation we are in and continues to the future. So now we are living in both the 4th generation and the 5th generation because they overlap. So the 5th generation comes with the invention of ULSIs, or ultra large scale integration. In the previous generation, meaning 4th generation, we had VLSI, or very large scale. Here we have ultra large scale. In these chips, we have millions of transistors and a single microchip. And also we have parallel processing introduced in this generation, meaning that a computer doesn't have only one processor. It can have several microprocessors that are used to divide the work of the computer. So here I want to give you a very simple example. Imagine you want to multiply 1,000 numbers by 2. So if you can divide the work between you and some of your friends, then the whole computation will be done in much shorter time. So this is called parallel processing, and it was introduced in the computer world in the 5th generation. This actually opened a whole new world about the ways one can program a computer and how different computers can cooperate with each other to do a specific task. So it enormously affected the speed of computers. So before, introducing parallel processing, only the number of transistors inside the chips would determine how fast the computer would be. If you remember, the Moore law, it said that the number of transistors would double every 2 years, and it would lead to computers that were roughly twice, 2 times more faster. But that trend with the Moore law couldn't continue after around the year 2000 because of the physical limitations of transistors and IC. It is still continuing somewhat, but not as fast as before. But then around this time, parallel processing was introduced, which opens a whole new door for making the computers faster. So the computers still continue this trend of consuming less power, being faster and getting smaller. And the fifth generation is actually also called the era of artificial intelligence, or AI for short. Artificial intelligence is about making computers that think and act like human beings. This is a very interesting topic, and we have actually a whole lecture about it. But to very shortly introduce that, I can tell you that in artificial intelligence, we talk about robots and robotics. We have neural networks that talk about how we can have computing systems that use some kind of networks like the networks we have in our brains. So the goal here in neural networks is to help computers learn like a human brain or an animal brain would learn. And we have computer devices that are so intelligent that can play games with you. We can have computer vision, meaning that computers can have sensors and they can see things and process what they have seen and do certain things based on what they have seen. For example, here in this picture, this robot is seeing the tomatoes in the farm and is picking up those that are ripe. And we have development of expert systems that can make decisions in real life situations. For example, we have self-driving cars, etc. And in AI, we have also natural language understanding and generation. In the fifth generation, we had other advancements as well. So the programming languages were shifted to a higher level. Besides the programming languages like before, for example, C++, Java, .NET, etc., we had computers that were powerful enough to understand human language. We have logic programming in which you don't have to specify the instructions at a very low level to say what to do on what data. Instead, in logic programming, you tell the computer what program has to be solved, and you don't give the detail about how the computer has to solve it, and it has to find a way itself. And for input and output devices, besides keyboard, monitor, mouse, etc., that we had before, we have now touch screens, we have speech input, because computers are to some extent understanding human language. And we have light scanner, etc. So the computers in the fifth generation became much more user-friendly, and they have many multimedia features. They are available for low prices, but still very powerful computers. And examples of it are needless to say. They are desktops, laptops, tablets, etc. So thank you very much for your attention to this lecture. If you have any question, you can reach us either through the forum on Studium. I have left the link here for you, or you can email us via Studium.